Welcome to the Lorenz Straub Award ceremony for 2021 and distinguished lecture today. Okay. My name is Lorenz G. I'm the director of Anthony Fossil Laboratory, okay. And it is always my great pleasure to start this ceremony every year. And this year we are going to celebrate the Straub Award for the thesis completed in 2021. Okay. And it is my great honor, okay, to welcome two of our distinguished guests, okay, Dr. Andrew Feldman, and he is the winner for this distinguished, very, very prestigious award. And also we have a great pleasure to welcome Professor Marccus Hendricks to visit us and to deliver this distinguished lecture. And well, okay, they are both from Maryland, okay, and I have just learned, actually, you know, they live very close to where I used to live. And before I moved to Minnesota, actually I lived in Maryland for several years. And I just learned that actually Andrew, where he lives is very, very close to my previous house. Okay, yeah. And the reason I'm saying this is because, okay, they are from, okay, East Coast, and well, today, you know, we Minnesotans did our best to put up a snow show for them to welcome. Yeah, okay, yeah. So, yeah, okay. And well, let me say a few words about Straub Award. Okay. And as you know, okay, Dr. Lorenz Straub was the founding director of our lab. Okay. And in the 1930s, okay, he had this great vision to establish this world-class hydraulic laboratory. Okay. So before that, okay, he visited Europe for about 2 years, okay, sponsored by ASCE Freeman Fellowship. And then okay, in the 30s, he joined the university as an associate professor, and in his 30s of age. And he came with this great vision of establishing this lab. And when he came to university, he already had this location identified, that is this St. Anthony Falls on this Hennepin Island. Yeah. And then he secured the funding for that, and then put into the design with his students, and in less than 2 years, okay, and this lab was established. Okay. So 84 years ago, and to be precise, 84 years and 12 days ago, the lab was commissioned. Okay, yeah. So you always remember, okay, November 17th is the birthday of St. Anthony Fossil Laboratory. Okay, yeah. So today, okay, we are going to celebrate this award. Okay. So after Dr. Lorenz Straub passed away, and then okay, many of his colleagues, friends, and and they established this fellowship. Okay. And in short period of time, okay, more than 100 individuals and organizations contributed to this foundation for Lorenz Straub. Yeah, okay. And ever since, okay, each year, okay, we have this award. Okay. And the award is for a previous particular year. And for example, for this year, we are looking at the PhD thesis in this research area, okay, completed in 2021, okay. And we solicited nominations from all around the world to honor Dr. Lorenz Straub's award worldwide, his impact worldwide. Okay. So for all the universities, all in all the countries, okay, each department can only nominate one thesis from that year. Okay. And both the advisor and the department head need to write nomination letters. Okay. And then okay, we have experts from other universities serving as the judges for this prestigious award, together with one professor from the University of Minnesota. Yeah, okay. And this year, our winner is Dr. Andrew Feldman. Okay. And Dr. Feldman, okay, he earned his PhD from Department of Civil and Environmental Engineering from MIT in last year, 2021. Okay. And his thesis topic is soil plant, I forgot the exact title of your thesis, but I know it is during interstorm and for the interactions, and it was really, really great work. And all the judges spoke very highly about your work. Okay. Well, without much ado, okay, I will, as a tradition of this award ceremony, and then okay, we will invite Dr. Feldman to give a short presentation about his thesis work, followed by short several questions, and after that, we are going to have our distinguished lecture. Okay. Yeah. Yeah.
Thank you. Yeah, so hi everyone. Can you hear me okay? That's good. Hi everyone, I'm Andrew. Really great pleasure to be here. I've never been to Minnesota before, and a nice welcome to snow. I find it to be quite pretty. It's great actually, it's really pretty. And yeah, it's the 2021 award. Sorry I wrote that, misspoke there, but it's a really great pleasure to receive this. It's really an honor. And a big thanks to my advisor as well for nominating, as well as my department head. My advisor, Dara Entakabi, is the main person to thank. He's had a large influence on this work, part of which we worked together, then the rest of it I went off on my own. So I'll show you two parts of that. But I'll focus here mostly on the component about the soil-plant continuum. I won't talk too much about land-atmosphere interactions, but I'll think a little bit about the soil-plant hydraulics from space. It sounds ridiculous, and I invite you to counter these arguments and do some experiments of your own with this, because I hope that this inspires some more work, actually, that we can see these things from space. So it's sensing water transfer in the soil plant continuum from space. Okay, not sure. There we go. So the big questions I'm getting at in the thesis is water, carbon, and energy cycles, and these are the cycles that really fundamentally describe our climate, our weather systems. If we want to know how the surface is changing or why there's a storm someday, we have to consult these cycles. And I was thinking about these in terms of a changing climate, thinking about global budgets, as well as land surface vulnerability. Under the question of why, what are the physical mechanisms that drive the land surface's response to variability and change? So not just how the land surface is changing, but what are the physical mechanisms, why? And some of the big findings here were that we really needed to go down to short time scales to see some of these mechanisms. At seasonal and annual time scales, we start to see some confounding factors, some interactions between different variables in the land atmosphere system. But interstorms these things started to become decoupled, and we could start to pull apart some of the drivers of some of the land surface response to variability. So interstorms here, it's the big motivation to look at this, is we can start to look at physical mechanisms. Another motivation is that interstorms themselves are changing. So storms not only are becoming, but they have become less frequent and more intense across the globe on average. So the plot on the left, this is 40 years of observations. This is not a model. This is pretty much from our observed record of rain gauges. We can see that the number of wet days per year on average across the globe is going down, shown in places in red. So there's less stormy days per year. But when it does rain, the intensity of the storms in the given day are stronger. So we get more intense but less frequent rain. And plants don't just like how much water there is that they get total over the year. They respond to the timing of the storms as well. So field experiments show that carbon uptake by photosynthesis changes over a year based on how storms are repackaged. They've done some experiments holding total amount of rainfall constant. If you repackage storms into more intense, less frequent, you can get GPP or photosynthesis in the year changes. So it's a motivation to look at the interstorm here. And global models, we might want to say, well, let's just look at a dynamic vegetation model. I'll argue that, first of all, they struggle a little bit with rainfall intermittency, and they don't really have a plant pulse response necessarily within them to really get at this question. So a reason to go look at observations. To appreciate this problem a little more, I'll just show you a schematic of what I'm thinking about here. In a current climate, you might have 5 rain events there on the top. This is just a schematic. And the blue is showing soil moisture varying. So soil moisture goes up after it rains and then decreases until the next event. But now in a future climate here, we're getting more intense, less frequent rain. We might have 3 rain events in a given month, but now they're stronger. And we get a more intense storm, so soil moisture really goes up. And there's a larger plant water uptake. But now we have a longer drying period. So there's a longer period of plant drying. So From that last slide, I showed that the carbon cycle is going to really it's not clear how it's going to respond globally over an annual scale. And it's now critical to think of this interstorm timescale. So I hope I've motivated looking at these individual pulses of rain and really break that down. A more specific question I'll talk about today is which plant function mechanisms are triggered during interstorms. So why do plants respond the way they do during a storm? And we can think of this even more broken down into how quickly does water move into plants after it rains? Is it really quick? On the left here we show, it rains in that gray bar, and then the time after pulse, water goes right into the plant, and then it dries over a couple days. Or is it like the right? Are plants, taking a couple days to take this water up, and the total volume of water? What does this look like? So how did we do this with satellites? How did we do this from space? Well, we consulted microwave remote sensing here. In fact, there was a speaker, Alex Konings, about a month and a half ago here, giving a long talk just about this. And I hope she motivated for you that we can look at plants from space and the water content within them. With these measurements, we can see not only, before we could only see the top of the canopy, but now we can see within the canopy with these microwave measurements. Not just the soil moisture on the top a few centimeters, but we can actually also see vegetation water content overlying on the surface. And the key to point out here is that, okay, this is NASA's soil moisture active passive satellite data here. The key to point out is that we can see this every 1 to 3 days. So now we can pick apart the interstorm timescale, whereas with MODIS and OCO, a lot of these other satellites that just see the top of the canopy, they're at that visible and infrared spectrum and thermal. They're very sensitive to cloud cover. But microwave, we can sample in all conditions, especially conditions outside right now. We can sample the surface, even though there's heavy cloud cover. So we can resolve individual storms. So this is the individual analysis here of each pixel. This is this kind of describes a lot of the work that's done here, how I looked at each pixel. So this, I'm showing an example here in South Sudan. This is SAFL grasslands, pretty classic case of very clean seasonality, a good situation to look at here just as an example. The blue is showing SMAP soil moisture in this grassland pixel, and you can see it varying in time, and it goes up over the summer months there. And we're looking at those red dots there. Those are the individual rain events. We're calling those out there. Rain event came through, pulsed the soil moisture, and then it dried down in time. And we were very interested in that green line, the vegetation water content. What is that doing after the storm? And I'm calling out a couple of those here, a couple examples in the bottom left. You can see, okay, the first one there, soil moisture is drying, vegetation water content decreases. The other cases, vegetation water content, in fact, is increasing. And so if you look at this over many cases, we saw this very consistent behavior described on the bottom right, where basically vegetation water content was increasing after storms. And then there was a water stress condition reached at a lower soil moisture value. I'll focus today mostly on the time scale here. So I'm going to take this information and translate this into how many days it took water to go into plants after a storm over the globe. And that's this image. So this is the time scale of plant water uptake after a rain event. And this is the median one. So this is what describes over many different events. This is the typical behavior you'd see. And the red there, hopefully it's red to you all there if the color's distorted, but the red there is mostly more humid environments. What that's saying is water went into plants very quickly, within a day. We couldn't tell how many hours because of our resolution of sampling, but it was within a day. Water looked like this in the bottom left. Plant water content increased immediately and then dried down after the storm. Whereas the blue, which mostly occurs in dryland environments, had this multiple day uptake of water content. And so part of this project was thinking about what actually should plants do. Is this just noise? Is this some ridiculous signal? We had to think about how quickly should water go into plants. And this required consulting some plant hydraulics. And in fact, the plot on the top left up there is the toy model, and the plant hydraulic model we looked at, in fact, was the previous Lorenz Straub Award winner, Sam Hartzell. I consulted a lot of her work as well as others to look at plant hydraulics here. And really, considering these conditions, under nominal conditions, water goes into plants very quickly in a lot of the field experiments. And if you look at the typical conditions, you can see a plot like this. where soil moisture goes up at time 0 there after an event, and plant water content in the storage follows that very closely, especially within a day. So water should go into plants within a day, and this is called pre-dawn equilibrium. I didn't mention before, but SMAP is sampling at 6 a.m. It's morning measurements, so we're really getting that time after overnight where we might have this pre-dawn equilibrium where soil and plants are equilibrating overnight. So that's what's described by a lot of those red pixels. I'll go back to this here. Those red pixels there really fit with the theory. Those are taking up water very quickly and then drying down after the storm. Soil and plant are coupled. But the drylands, and what's going on there? Why is it multiple days of water uptake in the drylands? That doesn't fit our theory. Well, it turns out that this is partially due to growth. In fact, plant water content is a volumetric parameter. If you have more water volume there, you actually have some growth that happened. And in fact, we corroborated this with some data from a daily leaf area index product that was a geostationary satellite. So this plot here is showing that the blue there, these are in drylands. These are multiple day uptake of water, typically over 3 days. So many days of water uptake after a storm. They were associated with growth. These happen mostly in growing season, and they happen typically after large rain events and wetter initial soil conditions. This built some evidence for us for what was going on here. This might be a growth response. When it crossed the thresholds, we're above a wetness threshold, and we get a very big response of vegetation. And this is showing the equation to show, okay, vegetation water content is in fact related to biomass. The amount of water that's there may indicate how much biomass is there, so there might be a growth signal associated with this. And this gave us widespread evidence for this, something called a pulse reserve hypothesis that was proposed mostly in very arid places, that ecologists thought that arid plants take up water only after a big rain event. It wakes up, it does its photosynthesis, there's a big pulse, it does some work storing carbohydrates into a reserve, and then it goes back to sleep. But what we found was that, okay, this indeed was a very strong response in drylands, but it also occurred in other areas as well, beyond just drylands, even up to subhumid areas. So there's a growth response after very big storms that we could see from the satellite. Now, what about these other cases of, there's these other 20 to 30% of cases that showed a 1 to 3 day uptake. There's no growth associated with those. What's going on there? Is that just noise? We looked at this. No, it's not. It's not noise. It wasn't very clear that was actually a noise signal. These actually occurred after drier initial conditions and smaller pulses. And so we coded up a plant hydraulic model that previous evidence told us about some dry conditions that are happening. There's a re-wetting, but it's not a very large re-wetting. So what's going on? Are there conditions where it can take multiple days for a plant to take up water after a storm? That's a little bit not fitting with that theory there, but are there other extreme cases where we can find multiple day, 1 to 3 day uptake of water in a plant? And in fact there are. They typically occur when plant resistance crosses a threshold. So basically xylem becomes restricted, or soil roots become constricted. Happens in drylands in some field experiment cases, but basically at high plant resistance, this plot on the left here showing over many simulations of a plant hydraulic model, when plant resistance gets a bit high, past that 10 to the 7th value there, we start to see many simulations showing multiple day uptake of water content in plants. And that's kind of the time series example there on the right, where the blue line showing a multiple day equilibration, not a fast equilibration there. And there's some dryland field experiments to corroborate that. There's actually several that occur in drylands. So we're actually starting to see some of these really neat mechanisms. So I'll conclude by saying, timing of rainfall matters for global photosynthesis. My current postdoc project is looking now, quantifying actually how much photosynthesis changes year to year based on these rainfall frequency changes. But a lot of this work here gave us the mechanistic tools to think about this. Rain pulses influence plants in ways of rehydration and even growth after storms. And not just growth in drylands, but actually beyond that too. Their dryland plants respond the most to pulses, but beyond that as well, there's a response, and that changes how they respond to rainfall frequency. And I hope I've encouraged you too, even if you thought this was ridiculous, to go and take vegetation water content from satellites and do different, it's really neat data. There's been some diurnal experiments out there. I hope I've convinced you with many pages of a thesis that there is a signal on a subweekly timescale. It's not just noise, as a lot of papers pre-2015 said. We can indeed use this data set for looking at plant hydraulics from space. So I hope I've encouraged you to do so. Thank you.
Fantastic work. We have time for a few short questions. Anyone wants to start first? Yeah. Okay, Brandon. Yeah.
Hey, really interesting talk. So the 1 to 3 days, just so I understand, is that it's just a very gradual re-uptake or re-wetting process that's causing the delay. So as it's becoming wetter, the resistance is going down and it's able to take up more. And when it's a really wet event, then eventually it can actually grow. Is that correct?
Yeah, there's basically, after a long enough drying period, the soil dries out. This is kind of when these cases happened, that there was this kind of multiple day repreparation that probably happened. And a lot of papers suggest that this was soil root related rather than xylem. But yeah, that's the idea. And I think that there's some field experiments to support that. I didn't show here, but yeah, that's exactly the idea.
Okay, thank you.
Yeah.
Dr. Ellis. Yeah.
Very nice talk. But can you give me like a bullet point on, so if our changing climate is, has more intense, less frequent events, does that mean that in the areas where you get a lot of growth after an event, you have less growth in that scenario or not?
Okay, the answer is it depends, but it seems that it's almost favorable for those locations to have the more intense storm, as opposed to other places that are typically wetter that don't have this pulse response. It's actually more beneficial for them to maybe have more smaller storms just to wet the soil overall. In fact, it's seeming like this. I'm just giving initial results from the follow-on project, but it seems like the dryland plants seem to benefit a little more from the more intense rains, that they can kind of have this growth period and then go back to sleep more or less, as opposed to smaller events that might not push them over that threshold to get them to respond.
Great talk, Andrew. I'm just curious, how would different plant type like C3, C4 would affect the response?
Yep. So that's a hard question for the scale, but if I'm not mistaken, C4 is typically in grasslands. I think a lot of there's a stomatal response a little more in those that will be more favorable to a drought response. I shouldn't say it. I don't know the direct answer. I haven't tested C3 versus C4. I'd have to think about that a little bit more, but that absolutely does, I think, will tell a difference between grasslands and some shrub, and even grasslands versus some crops. That might explain some of the differences between some of those responses, especially during the drying period, how fast they lose water. I can't comment on how C3 or C4 would. I should look at that a little closer. Yeah.
So Joanne Boucher wants to know, is the slow uptake process in drylands true for both native dryland plants and non-native, potentially irrigated crops or plants?
Okay, irrigated is tough. I don't know if the pulses that we're seeing there that we're sampling are actually rainfall experiments, or sorry, natural rainfall, or if they're irrigation. They kind of get lumped together. Actually, can you repeat the first part? I'm trying to remember the first dichotomy question.
Slow uptake process in drylands true for both native dryland plants and non-native, potentially irrigated crops or plants.
Yeah, so this is unfortunately a 30-kilometer resolution satellite. So we're averaging all of those, unfortunately. I would guess we would see some differences between shrubs and grasses. I'm not sure about the native, non-native, and that could be shrub-grass related differences, but I couldn't see that here, unfortunately. So thanks for the question, actually. That's a very good one. If we had higher resolution data, we could probably tell a little closer.
One last question.
Oh, okay. Thanks, Andrew. So I saw that you separated your results and kind of broadly into dryland category and then non-dryland category. And I was wondering, since VOP is something that captures changes in both biomass and water content, right? Whether you've tried to attribute the VOD changes into like one or the other by maybe separating your categories further into areas that had higher biomass or lower biomass, or maybe some other ways of addressing that.
Yeah, mostly did that with the leaf area index. So there's a geostationary satellite in Africa that samples daily leaf area index. It's a little better than a little more rapid sampling than from MODIS. So we were able to use that to see some of the rapid growth and to partition some of those types of events. We didn't do that spatially as much, and I have to think a little bit about that difference between a high biomass versus low biomass region, if that would show a difference. But we mostly did that with the leaf area index product that appears in the results here.
Thanks.
Yeah.
So, well, it's a really great talk, great. Meanwhile, okay, I would like to present this award certificate to Dr. Feldman. And for our award ceremony, so each time we invited a distinguished researcher from outside, mostly, to a keynote talk, okay, about this. And well, this year, okay, we have another distinguished speaker coming to SAFL to visit us and to deliver this wonderful talk, okay. And well, okay, next, I'm going to ask one of our students to introduce our speaker, and the student is Vinny well, I'm always on first name base with Vinny, and how to pronounce his last name? Teguchi, right? Yeah, okay, yeah. And sorry, Vinny, about that. And I'm just too familiar with you. Yeah, and as you know, okay, SAFL student body has been very active in every aspect of the lab life, including our seminar series. Yeah, so our students give suggestions about the potential seminar speakers, and they are involved in the selections of the seminar speakers and in the invitation and also in the hosting of the seminar speakers. Yeah, okay, so today really, okay, it gives me great honor to invite Vinny to introduce our speaker.
Thank you, Leanne. Can everyone hear me? I'm assuming that's a yes. I can't actually hear the feedback, but yeah, as Leanne mentioned, my name is Vinny Taguchi. I'm a PhD candidate in civil engineering at SAFL, although nowadays I find myself physically in North Carolina. So unfortunately, I'm missing all the beautiful snow, and I'm so sorry that I can't be there together with everyone in person for the Straub seminar. But as a student, I discovered Professor Hendricks's work about 3 years ago, and it's just been very inspirational to me. The way he finds these interactions between the engineering and the science that we're doing at SAFL is such a interdisciplinary place, but there's also the aspect of the human impacts and interactions that occur with our work and with any work that we do. So it's very exciting to see someone that's pushing the scholarship and building those bridges across fields. So for those who don't know, Marccus Hendricks is a associate professor of urban studies and planning at the University of Maryland, College Park. And he is also the director of the Stormwater Infrastructure Resilience and Justice Lab, which is a pretty unique place. And I hope this is just the start of interactions between Professor Hendricks's lab and SAFL. To date, Marccus has primarily worked to understand how social processes and development patterns create hazardous human-built environments, vulnerable infrastructure, and the related risks in urban stormwater management and flooding. Other work has focused on technological disasters, namely fertilizer explosions, and structural damage assessments and recovery trajectories, as well as cascading events such as wet weather events that overwhelm sanitary sewers and cause overflows, household backups, and contamination. His work emphasizes participation and action that uses methods including photography, visual inspection, and environmental sampling. For example, he developed a participatory assessment technique for infrastructure that provides a community-based approach to assess the capacity and physical condition of stormwater and other infrastructure systems. This application of community science was the first of its kind, connecting flood risks from stormwater runoff to the infrastructure systems that are supposed to provide physical protection. So without further ado, it is my honor to turn it over to Professor Hendricks.
There we are. All righty. Thank you all so much for inviting me and having me here, and thank you specifically to Vinny for throwing my name in the ring of, I'm sure, a number of folks that could have been here to deliver this talk this afternoon. And I'm especially delighted because, you know, I've done a number of invited talks over the years at my time at the university, but this is the first time that had the label of a distinguished lecture, right? And so, you know, I'm not sure, maybe it's because I recently received tenure, and so post-tenure now my invited talks will have that distinguished label. And I've also just want to say thank you to Claire and the other, you know, staff and students who have, and faculty who have engaged me throughout the day and literally rolled out the white carpet, if you will, in terms of the snow that we're seeing. This afternoon, really picking up where Andrew left off, and you know, he was talking about this soil-plant continuum, and I want to talk to you all about another SP continuum, but a social-physical continuum, right? In terms of the relationship between some of these physical outcomes and the influence of these human and social processes that impact directly these physical outcomes. And I struggled all day trying to decide exactly which project I would focus on and talk about, and after meeting with several different faculty and students, some folks were interested in one project, others were interested in another, and so I figured I would do sort of a rapid fire of projects and give you all little nuggets, a little bit about several different projects that are operating out of my research lab at the University of Maryland. And so, social physical infrastructure and environmental risks, people, pipelines, and pathways. And, you know, when I give talks, I normally, before I dive into the research, I like to give you all some insight into who I am and how I got involved in this work. Does anybody recognize this skyline? Man, and so that, you know, does away with my punchline in terms of this is one of the more recognizable skylines in the country, maybe not so much, right? This is Dallas, Texas, right? Where I was born and raised, and prior to me asking you all that question, I used to think it was one of the more recognizable skylines in the country. And, you know, born and raised in Dallas, over the years, done some notable things in terms of urban revitalization, and ways in which they've transformed the urban built environment in terms of addressing some of the challenges that we're facing, and also addressing some of the social aesthetic issues, and just a beautiful city, in my humble opinion, in terms of the place that I grew up. However, my everyday experience growing up in Dallas wasn't necessarily reflective of that skyline and that charm that I mentioned. I grew up in a marginalized Black and brown community in inner city Dallas, a community where most scholars would consider to be an environmental justice community, a community where that was surrounded by industry and petrochemical facilities, communities where, you know, women-headed households and low wealth residents were surrounded by bad streets and it flooded all the time. And every sort of environmental justice related or environmental risk issue that you can think of, from water quality issues to air quality, my neighborhood and community faced it. Specifically, I grew up on a street by the name of Stanley Smith Drive, and perpendicular to my street was a street by the name of Prosperity Avenue, right? The irony, because in terms of the stage that was set for the lived outcomes and experiences of my community were the complete opposite of prosperous, right? And in fact, I would notice, you know, again, certain environmental challenges that my community faced. And when I traveled across town to other communities, particularly north of my community and more white and affluent communities, I would notice that there was a stark difference in the quality of the built environment. And the interesting thing about being a planner and having a stake in a built environment, when you drive across cities and you see the changing demographics, you can usually see the changing reflection in terms of the quality of that built landscape moving across communities within any given place. And I witnessed that firsthand growing up in Dallas, and that was sort of that lived experience and intuition that planted the seed for my current research program and the work that I've been doing at the university. And so, as mentioned, I direct the Stormwater Infrastructure Resilience and Justice Lab, and we focus our work within 4 general domains of planning, between infrastructure planning, participatory planning, hazard mitigation and disaster recovery planning, and broader environmental planning. And at the nexus of these 4 domains of planning, we ask questions about the ways in which infrastructure affects the natural, built, and social environment. We try to understand the role of infrastructure in modifying different types of hazards and risks, and even public health outcomes. We think about infrastructure design between gray and green systems and what that means in terms of resilience and adaptation or sustainable development. We also understand that our work is limited in terms of impact without having meaningful civic participation and action, specifically through community science, in terms of overseeing and provisioning a variety of infrastructure assets. And last but certainly not least, we anchor all of this work within an equity and environmental justice framework in terms of public works management between procedural, distributive, and restorative justice. And within the lab, one of the areas that we focus on specifically in terms of hazard risk is this phenomenon of urban flooding that's increasingly being discussed both in national reporting, headline news, as well as the academic literature. And based on, you know, some of the things that we've witnessed, two particular case studies include Tropical Storm Harvey. And I want to be clear in saying Tropical Storm Harvey because of the disastrous impacts that Houston faced was actually when Harvey downgraded from a hurricane to a tropical storm that was largely a rainfall event in 2017, where some parts of Houston received more than 50 inches of rainfall. Total damages were estimated upwards of $120 billion. There were 68 deaths directly responsible from the storm event, the largest amount of deaths since 1919. And an interesting stat is that 68% of the flooded homes are actually outside of the 100-year riverine floodplain where we normally anticipate flooding and flood impacts. If you take a trip northeast to the mid-Atlantic, where I currently reside in Washington, D.C., we've also had our fair share of urban flooding events. In fact, in 2019, we saw nearly 4 inches of rainfall. A month's total fell in just 1 hour. Some roads took on as much as 5 feet of water. More than 100 rescues were made. Thousands of households were actually without power. And to make it real for you all, we've also seen incidents of flash flooding and urban flooding here in parts of the Twin Cities. In August of 22, events where we saw water sweeping through parts of the Twin Cities, leaving drivers stranded. streets flooded, buildings damaged, 4 inches or more rainfall fell in just a 1 to 2 hour time span, down trees, stalled vehicles. And so these circumstances and issues of urban flooding are pervasive, and we're seeing these circumstances across the globe. And so some of the commonalities that we've begun to recognize in terms of what contributes to these urban flooding events is that, one, we know that rainfall is a major contributing factor in terms of pluvial events, moving water inland and impacting beyond the coastal or riverine flood zones. We also know that the amount and location of impervious cover, particularly in high density areas and urban areas, is increasing the amount of stormwater runoff. And lastly, we also know that when it comes to current status of stormwater infrastructure installed in these urban environments are unable to cope with the amount of stormwater runoff leading to these flooding events. And stormwater infrastructure is really where I want to focus for a second in terms of our conversation, because within sort of this climate crisis and these increasingly urban flooding events, we're also in the midst of an infrastructure crisis. From collapsing bridges in California to overflowing storm drains in Houston, a lot of our systems are past their prime, and decaying infrastructure is ubiquitous, right? In fact, the American Society of Civil Engineers has consistently scored our infrastructure at the national level below a failing score. In their most recent report card, we barely passed in terms of a C-, just shy of a failing score. And in recent years, with the Biden administration and this historic infrastructure bill, this phenomenon of this infrastructure crisis has been well documented. It wasn't that way when I first started doing this work. But for anybody who studies disaster or crises of any kind, fundamentally has to understand that social stratification is inherent within any crisis or disaster. However, little to no attention has been paid to where and on whom the burdens of this decaying infrastructure fall heaviest, and that's where my work comes into play in terms of leaning on these two bodies of literature between environmental justice and social vulnerability to disaster. And environmental justice, corroborated evidence makes the case that the nation's environmental laws, regulations, policies haven't been applied fairly across all segments of the population. Social vulnerability to disaster is complementary and talks about how social stratification based off of race, income, ability, gender, age, nationality, among other factors, contribute to differential risk and impacts from disasters. Specific mentions of infrastructure across these two bodies of literature come from Dr. Robert Bullard in '94, where he really challenged the nation to redefine environment to include infrastructure. Dr. Shannon Van Zandt in 2012 talked about how infrastructure and other environmental features can modify vulnerabilities and risk. Dr. Jacoby Wilson in 2008 talked about the failure of municipalities to install up-to-code sewer and water infrastructure can lead to vulnerabilities in these systems, particularly among poor people of color residents. And so effectively what we have here, and something that I want to drive home if you don't remember anything else that I say this afternoon, is that we have these larger social processes between historic legalized redlining and racial zoning, chronic unemployment, substandard housing, residential hypersegregation in 2022, ongoing economic disinvestment, discriminatory planning, poverty, that fundamentally have consequence for these infrastructural processes in terms of the inventory, condition, distribution of critical systems. And I know in a room full of engineers, we like to think, oh no, these physical systems operate in a controlled manner, right? And they sort of lack the influence from these human decisions and social processes, but that's fundamentally not true in the case, right? Because those social processes have influence, again, on inventory, condition, distribution, even the types of materials and equipment that we use to construct and develop these infrastructures, or even the ongoing maintenance and rehabilitation decisions that we make regarding these systems are fundamentally a matter of social and human processes and decisions. I further unpack and make the case for this socio-physical continuum in a piece that I published last year titled Unequal Protection Revisited, Planning for Environmental Justice, Hazard Vulnerability, and Critical Infrastructure in Communities of Color. And I really sort of leave or end that piece with this really complex conceptual framework that really connects social variables of social vulnerability and environmental justice to some of these neighborhood factors and inequalities that we see manifest, that are also connected, again, to these critical facilities and infrastructures that exist in communities that are supposed to provide fundamental utilities or lack thereof that have, again, consequence for hazard, risk, exposure, and even recovery. And I also want to pause parenthetically to say, you know, if my colleague, Dr. Fiola Jacobs, who is over in the Humphrey School, what she would say is that we use these variables of race, ethnicity, class, and gender as proxies for racism, classism, sexism, right? Because black and brown folks, poor folks aren't inherently vulnerable to these circumstances, but are marginalized in ways that lead to some of these disastrous outcomes. And so the first case study that I want to talk about that sort of demonstrates the ways in which these communities might be subjected to environmental injustice by way of infrastructure is looking at a case study in Washington, D.C., our nation's capital, you know, 700,000 people as of 2019, located the northern shore of Potomac, and its tributaries between the Anacostia, between Maryland and Virginia, 40 inches of precipitation annually across a 60 square mile area. And DC, again, has had its fair share of disaster declarations and flooding events over the years. When it comes to the systems that are deployed to service Washington, D.C. residents in terms of stormwater, they have two types of systems. They have an MS4, a municipal separate stormwater system, and some parts of the district have a combined sewer system. And between these systems, you know, the lab, we study everything from the distribution of the pipelines between the systems to the quality of water that's coming out of the outfall and distributing and depositing into the local bodies of water, to above ground surface level structures that convey and feed the water into the pipelines, to even the damage to the homes and structures. With this particular study that, you know, one of my doctoral students in the lab is leading, we wanted to sort of map and show the distribution of both pipeline and capacity of the stormwater systems in Washington, D.C. And with this map, you can really see a diagonal line of really segregation between the darker shaded boundaries are communities of color, and then when you look at southwest DC, you can start, the lighter colors represent more white and affluent communities, and there's literally a diagonal line that divides. And then when you look at the circles in terms of the amount of pipe length and capacity across these communities, you can start to see some differences. Obviously, we can't depend entirely on a map, and so we deploy these empirical models, right, where we sort of show, based off of again, social vulnerability indices and other covariates, how they influence the distribution of pipelines. And I have the significant variables highlighted in these red outlines, and we see that social vulnerability came back statistically significant, as well as a few other variables in the model, including the impervious rate. The same holds true when we move from pipe length to pipe area, which we're using as a capacity proxy, and really sort of a pretty robust model with a decent R-square that's coming back from these models to really show, in terms of stormwater infrastructure and underground pipeline installation, they haven't kept pace with above ground development and imperviousness. Essentially, what we're seeing is that as the amount of imperviousness increases across communities in the district, we're seeing a reduction in the amount of pipe length and capacity. And I don't think that this is unique to DC. Again, I think I was talking to several people throughout the day in terms of stormwater systems being a stepchild of utilities and infrastructure, and it costs so much to sort of break ground and install pipelines and things things like that. And so we've done a lot more damage and development above ground than we've done to address some of those issues and additional runoff in terms of pipelines. Another major takeaway is that socially vulnerable communities on average have less pipe length and capacity relative to non-socially vulnerable communities, and thus lack conveyance pathways and potentially are more at risk of some of these flooding scenarios and outcomes. I want to transition a little bit to talk about and say that issues of urban flooding are not just an issue of water quantity, but water quality. Some of my other work in Baltimore is really addressing this issue of wet weather, extreme wet weather events, not only overwhelming stormwater systems, but also overwhelming adjacent wastewater systems and causing backups and contamination in people's basements and homes. And these red dots represent just the number of basement backups that happened in the city of Baltimore between 2017 and 2019. Specifically, according to the Chesapeake Bay Foundation, since 2011, there have been more than 3,900 individual sewer overflow events, 110 million gallons of raw sewage spilling into people's streets, homes, and streams throughout Baltimore and eventually into the Chesapeake Bay. And within this project, exploring this issue of sanitary sewer overflows and basement backups, several activities between a literature review, a spatial analysis, as well as in-depth stakeholder interviews and some household surveys and sampling. And literally this summer, we were knee-deep in raw sewage in people's homes in Baltimore doing some of this sampling for both traditional and non-traditional waterborne bacteria. And some really incredible findings that we're going to soon announce and publish. And I don't want to get the details just yet because we anticipate it being literally a toxic situation in terms of the amount of press and media that will come about from the announcement that we make. But a very precarious situation in terms of some of the live bacteria that individual Baltimore households are being exposed to by way of these basement backups and overflows. We're doing some lab modeling and testing to confirm those things, as well as, again, sort of connecting those things through lived experience and perceived risk in terms of the household surveys. When it comes to the in-depth interviews, that one of the activities as a part of the project, one of the preliminary things, or a few of the preliminary things that I want to point out in my conversations with stakeholders all the way from the local level, DPW, up to the EPA, is that we have these legally permitted demarcation lines for a physically interconnected system. And I know I was sort of going back and forth in terms of the language that I want to use for this preliminary theme, but to break it down further, essentially we have this invisible property line to demarcate responsibility in terms of infrastructure failures and collapses and whose responsibility it is to address some of these issues for a physically interconnected system, meaning that there might be collapses and cracking and pressures on the sewer main that causes pressure on the lateral line on a private property side, but technically if it happens or the damage or collapsing happens on the side of the private property owner, it's their responsibility regardless of what's going on in terms of the sewer main and the public right-of-way. And that's problematic in many of ways because, again, we can't have these invisible, politically demarcated lines for a physically interconnected and interdependent system. And I think in terms of engineering and public works, and one of the challenges that we're going to have to address at the end of the day is how do we remove this invisible barrier to make sure that we respond to these infrastructure systems holistically and in the ways that they're constructed and designed through their interconnection. Another thing that I wanted to point out is that we have explicitly illegal laws in terms of discharging and habitats, but those laws are a bit murkier when it comes to homes. And so when it comes to the EPA Clean Water Act, it's explicitly illegal to discharge certain effluents into the Chesapeake Bay, but if that discharge happens into people's homes, there aren't explicit laws in terms of what's required from the city or even the federal government in terms of responding to these things, right? And so another challenge in terms of the ways in which municipalities have been getting around not fully addressing some of these issues of backups and overflows. Something else that I've learned is that we have this stigma with stink, right? Residents are suffering in silence dealing with these basement backups and overflow issues because they don't want to announce to the world that they have raw sewage in their homes. And so when we don't know about these things and they suffer in silence, there's not a voice and momentum to fundamentally address these issues, which is another challenge in terms of community engagement that we have to consider. The last thing I'll point out is that we talk about this infrastructure crisis in terms of the physical systems, but we also have an operator crisis, right? Engineers and folks who work in public works and the operators that respond to calls to 311 aren't aware of the full extent of the problem, and they don't even know the full extent of the possible remedies and solutions in responding to the needs of residents across communities. And so not only do we have to address the issue of no service in terms of investment and rehabilitation, well, we also have to address the issue of what folks are saying and how they're responding when residents call in to the city. The last thing that I'll talk about is that, you know, again, talked about urban flooding as an issue of water quantity, and also mentioned that urban flooding has consequence for water quality, but it also has consequence for what we're calling these cascading events or NATEC events, where natural hazards trigger these technological disasters. And we saw incidents of this in terms of Harvey and some of the flooding that happened on some of these industrial sites and caused leaks and explosions and fires as a result. And me and one of my colleagues studied some of the damage impacts from blast and recovery trajectories in a rural community in West Texas, which we think can hold true for other blast and damage impacts from a variety of events. And so fundamentally, what we have here is that usually when it comes to smaller or more rural communities, they don't have the fine methods and data that we typically see in larger cities. And so we have to be a little bit more creative in terms of developing that database to be able to address some of the challenges that they're facing when they experience disasters. And so what we did in order to address this parcel level research, we took a very practical method of taking pictures, right? Again, for a community that doesn't have knowledge of you know, how to do some of these more sophisticated modeling and methods, but something that they are familiar with is simply taking pictures, and how can we apply metrics to these pictures to effectively evaluate the damage and recovery trajectories for these communities. And so we wanted to understand exactly how this could work, what it would look like, and how it could support communities. And so immediately after the explosion in West Texas, it was actually scheduled for Google Street View to come through and take the pictures. And they allowed Google Street View and nobody else to come in and actually take the pictures. We were looking online and discovered that the pictures were going up. Google didn't sort of have any restriction immediately of uploading the damaged structures onto Google Street View. And so we immediately started screenshotting and downloading the pictures from the front and one picture from each side of the parcel to get a picture of what the damage to the structures in the community looked like. About a couple weeks after I finished downloading all of the images, the feds required Google to pull the images and redo the street views at a later date. And so we got the images just in a nick of time, and we were able to show, demonstrate some of the damage that existed. And most of the damage happened between no damage or minimal damage in terms of a 0 to a 3 score, but we did see some structures that were completely destroyed and damaged. And in the models, what we were able to show through a basic OLS model, and yes, the data was sort of ordinal, but we chose to use an OLS because it didn't violate the assumptions, because the data was more or less continuous in terms of the stages between the levels of damage. And just sort of an aside for, you know, the doctoral students in the room, when and if you can use a blue model, best linear unbiased estimates, use the simplest model, right, in terms of your estimations, as opposed to using an unnecessarily sophisticated model. And so that's what we were doing. And so what we were able to find is sort of, you know, basic assumption that the closer you were to the plant, the more likely you were to experience damage and to be impacted. However, when we shifted from modeling the damage to modeling the recovery using a different scale, what we were able to show is that although proximity to the blast was the best predictor of damage, the best predictor of recovery was actually the pre-event assessed value, right? And so the higher the assessed value in a community, the more likely they were to recover from the blast, which fundamentally has some social implications in terms of who's able to afford what. And even with minimal damage, some communities went 3 years without actually fully recovering from the blast event. We also saw that most often, if you didn't recover within 14 months of the event, the likelihood that you would recover decreased significantly, and that rebuilding slowed dramatically thereafter. I'm running out of time. Again, these were sort of, I was trying to decide what I wanted to talk about. This last project is that a pathway. You know, my title of the talk was you know, pipelines and pathways in terms of these socio-physical dynamics. But I want to leave you all with some encouragement in terms of there are opportunities to bring lay community folks and residents along with us as we make these discoveries and we investigate these challenges within what I call the human-built environment. And essentially what I did was that I mobilized a group of community residents on the east end of inner city Houston as community scientists and adapted a technique that engineers use in departments of public works to evaluate infrastructure, and I trained them on how to do that process. But at the beginning of this process, I understood that there would be people that would push back in terms of how can we trust and know that community-derived data is valid and reliable. And so in order to address that issue and that doubt on the front end, what I did was I set up an experiment by which I trained or I tested the data derived by community scientists against trained engineers and LiDAR technology, and I was able to demonstrate that there wasn't a statistically significant difference in the quality of data between these three separate groups, really demonstrating that community folks with a little training and a lot of intuition can be engaged on these fronts of infrastructure in terms of quality and condition. And so, you know, the major takeaways is that when it comes to equity and justice and infrastructure, we have to think about it along the lines of procedural, distributive, restorative, and data justice. We also have to understand and recognize that the built environment is a continuum of social circumstances. We also have to sort of understand that infrastructure dynamics have implications for risk exposure, ecological, public health outcomes in terms of water quantity and quality. Cascading events are new normal. We're seeing it all across the country between Texas, the Carolinas, and beyond. And you know, there are social and practically innovative pathways that are being developed by myself included that refine the planning and engineering processes that we do for environmental risk and community science, civic participation. These university community service learning partnerships are a pillar in planning, need to be a pillar in engineering and public health, and in fact is a democratic gateway to a more informed, healthy, just, and resilient society. Thank you all so much.
Thank you so much. This is really great work and a great talk. Yeah. So now the floor is open for questions.
I know, where do you start?
So a lot of these problems start with the redistribution of the taxes, right?
Yeah.
Is this something that do you think is going to change? Because to me, that's the major issue preventing having a good system of infrastructure pretty much everywhere.
Sure. Yeah. No, that's a great comment and question. And I think that I tell my students and folks all the time, if you really want to understand the quality and condition of the broader community, including infrastructure, you can usually look to the quality of housing. And if you want to understand the quality of housing, you can usually look to who lives there in terms of race, ethnicity, class. And so along these other continuums in this social physical, we see that most often lower wealth people of color typically occupy communities in disrepair that fundamentally impact the tax base that lead to funding pots for capital improvement and investment. And I think that if we continue along this trajectory of status quo business usual, it won't change. But we have to be very intentional of understanding disparities that exist by way of these social processes and be intentional through an equity lens to address places that, again, don't have those tax bases and provide that additional support to make sure that they're able to keep pace with other communities that might have that tax base through larger, more affluent housing and things of that nature.
I have a question for you from online, so I'm gonna read it. It's from Hannah Stesberg, and they're asking, what is the most effective way to prevent the rich from protecting themselves only from environmental hazards by externalizing costs and harms to those less able to defend themselves or move out of harm's way into richer neighborhoods, by using more energy, by relocating? Do we need to increase home ownership and or establish more rights for renters, for example?
Oh, that's a loaded question. I think if I were able to answer and do justice to that question, I might retire, right? Because I think I could spend the rest of my career really addressing it. I think that people lack inspiration because of a lack of experience, right? And when things aren't impacting them, if a tree falls and there's nobody around to hear, does it make a sound? Likely, but does anybody care? Probably not, right? And I think that's the case when it comes to affluent communities that see disasters from a distance, but don't have the same skin in the game as folks that have been historically impacted by them. And I think with these, with the degrees of separation of folks that are being impacted by flooding and other climate-induced hazards, that degree of separation is decreasing in terms of you yourself or somebody that that's being impacted, and so you tend to start to care a little bit more. And so I think the circumstances and where we find ourselves in this climate, is that people inevitably will have to have skin in the game to address those issues. And then, again, we start to work towards something that, again, impacted communities have been raising hell about for a long time, but have received little to no attention. I also think that people are just recognizing that there are certain communities that have been, catching hell over the years, and it's being more obvious and evident, and again, developing more and more corroborated evidence to demonstrate that fact. And whether, whether it's a lack of opportunity to afford housing and live in a thriving community, or just, being overburdened by toxic and waste treatment facilities, that people are seeing it in real time through videos and live footage, and I think that pulls at your consciousness a little bit more than when it's out of sight and out of mind. I also think that, again, we have to sort of anticipate some of these circumstances on the front end, even as we make improvements to the built environment through the installation of green infrastructure. We have to anticipate and mitigate displacement on the front end by making sure that we provide opportunities for residents to have a financial stake in the place through examples like a community land trust. So that way, by the time installations are made, improvements are made, businesses do come in, that they have some level of protection and stake that might help to reduce the level of displacement.
So thanks again. I've sketched out a number of questions, but I think one that's short enough to read out right now. So we often talk about urban flooding being driven by climatic related events. So you talked about Harvey. But then it sounds like from what you said that we can expect Harvey's impact to be very different on different communities because we have different drainage infrastructure, which relates to poverty, which relates to systematic advantages and disadvantages. And I'm curious how much each of those is on the scale. Number one. And number two, I'm curious about something else because this is a point at which maybe some rich folks and more white folks have some of that problem and see enough of it.
Sure.
And I'm wondering about the use of those things to start to create community that goes beyond those neighborhood and class borders.
Sure, yeah. No, great question. And, immediately I want to say that, we know, in fact, that there are a number of factors that contribute to urban flooding. The weights of those factors, I don't think we've gotten to that point of being able to apply those weights in terms of which ones have the most impact. But what we do know is that, again, the reason why I say the human-built environment is because humans have fundamentally changed the hydrology, the imperviousness, the ecological environmental dynamics of our planet in ways that are irreversible at this point, and are ways that very much so contribute to the outcomes that we see. And prior to human development and settlement, there were natural ways of managing water that no longer exist. We have this concept in planning where we talk about smart growth, but we do smart growth in dumb places when we build mixed-use housing in an environmentally sensitive place, right? And so we still see some of these damage and exposure outcomes that we see everywhere else. And so I think that we have to take some accountability in terms of, again, the decisions that we make in terms of the built environment and sort of rewriting that narrative in a space that reduces the risk and incorporates some of the more beneficial features that manage some of these risks. Does that answer your question?
I think that's on the way, yeah. Thank you.
Yeah, okay.
The chat. So I'm going to start with Jesse Cooley asks, can you talk about best practices for community engagement, how to build trust and make connections for authentic information sharing and hearing of underserved voices? How do you engage authentically when so many folks have understandable mistrust for government?
Ooh, that's another loaded question. A question that I think that I can spend an entirely different lecture talking about in terms of what does principled engagement look like? What does a covenant with communities look like? How do we eradicate extractive research? How do we build trust and relationships with communities? And I have a set of principles that I go by that was passed down to me from one of my mentors, Dr. John Cooper at Texas A&M, who's now the VP for community engagement at A&M. But yeah, I think from the very beginning, you have to set up this process where you engage early and often. You create opportunities for reciprocity and feedback, that you really think about long-term relationships instead of one-off projects, and making sure that you have succession plans in place for when and if you transition, you graduate, you get a job, that the challenges in communities don't come to an end because you get a diploma in your hand, right? And so making sure that there are faculty and other folks that are able to tap in and continue their work. I think making sure that what is developed and adopted is mutually agreed upon. Again, that really sort of allowing communities to set the rules of engagement in terms of how, when, where, and why they might engage and benefit. And like I say, a number of other sort of principles that I can talk about in more detail, but I will have you all here for another 30 minutes.
I have more questions in the back, but if anyone would like to ask one in the audience, please just let me know and I'll pass over to you. So Vinny wants to know, what advice could you give to those who might feel like these topics are important, but unfortunately fall outside the scope of their work or projects?
Yeah, good question, Vinny. And I would argue that I don't think that they fall outside the scope. Is how you define the parameters and the scope, right? because a lot of folks might argue that, you know, these social issues have nothing to do with physical engineering, when I sort of hopefully made the case that they fundamentally do. Again, I think that when we develop physical solutions that then operate in a social world without considering social conditions, we undermine the engineering and the time and effort that we're putting into and developing these solutions. And so I think, and I'm hopeful that that is becoming more and more obvious as we move into really sort of these, you know, dynamic circumstances of seeing social, physical come to a head in real time. And I would just say, you know, stay encouraged and stick to it, because, you know, when I started my work, my dissertation was titled The Infrastructures of Equity and Environmental Justice. And when I was on the job market with interviewing at planning and engineering schools, nobody was interested in what I had to say. You fast forward 3 years later, and I'm declining invited talks, right? Because now everybody has discovered that, oh, wait, yeah, you know, that there is a connection and we have to pay attention to it. And so it's really about staying true to yourself, being consistent, not giving up on your ideas, despite what other folks might think. And I was also, I think, telling some of the doctoral students at lunch that my master's is in public health. And during that time in the master's program, it was 2010, and everybody was focused from public health, was focused on chronic illnesses and Healthy People 2020. And here I come wanting to study infectious disease and acute illness. And everybody was like, what the hell, Marcus? Nobody is interested in that stuff, right? And my master's paper and thesis was about how do you leverage mobile health clinics as vaccination opportunities for underserved and low access communities. And then fast forward, right, 10 years later, and we're in a global pandemic, and we're seeing some of the things that I proposed in my master's paper that I didn't publish because folks didn't encourage me to, because they were disinterested, now sort of getting a lot of attention and traction. And so I think sometimes there's a lag in terms of people who see value in novel work. But then I think, again, if you're doing the science in the right way, it's grounded in theory and a conceptual framework, that it makes sense while you're asking those questions and you're doing what you're doing, that it'll finally catch up in terms of acceptance of the work and folks that place value on it.
Nikki wants to know, what sort of things were citizens able to assess with the infrastructure inspections, and how did you recruit volunteers?
Yeah, they assess pretty much all of the parts, all the features of the assets that were above ground and that could be visually inspected above ground. And so whether it was a open ditch or cross, you know, a culvert or cross drain pipe or inlet, based off the physical designs and what those things ought to look like in terms of in-service operation, we had a number of performance standards that spoke to whether or not, you know, from a visual inspection, the assets were meeting those standards, and the citizen community scientists responded to those performance standards through a pass or fail. And then we have an algorithm that develops a sample unit score and a composite score that ranges from 0 to 100 in terms of 70 and above passing and below 70 failing. And they were able to, again, respond to those performance standards. And we were able to derive a score to show, you know, empirically what the condition of their infrastructure was. And so, yeah, I mean, several papers have been published about it, and I'm happy to share those, and feel free to email me about specific performance standards in terms of what they were evaluating. Yeah, I know people are probably tired. I'm happy to wrap up. Yeah.
Oh. Well, yeah.
Thank you for your talk. This might not be quite directly related to what you're saying, but I was just thinking about the concept of managed retreat, especially for folks who don't have the resources, like seeing what's happening in Florida, for example, in the past month. Yeah. Concept of home and like the cultural identity of belonging to a place. How do you value that in your research and when you're talking to people in the communities? I suppose as an engineer, how should we put the price tag to that?
Yeah, no, that's a good question, and I'm not sure that I can answer because there's an entirely different body of literature that talks about place attachment and managed retreat that I don't think I'm equipped to sort of respond to, because most of the time the places that I've been working in aren't places that realistically would be in a place of managed retreat, and so it's kind of more like how do we adapt in place, and so that's where most of my work has been done. But yeah, I think you're right. When it comes to, you know, cultural considerations that have to be made in terms of place attachment and you know, what that means to different people and communities and whether or not, you know, those things can be replaced in a new place, right? A new geographic location. And those are all considerations as we sort of propose some of the solutions to respond to these environmental conditions.
Great. Well, I'm really impressed by the large amount of questions and for the consideration of the duration of our ceremony. How about this? I will allow one more question from the audience and one more question from online.
Very good.
Yeah. And afterwards, feel free to yeah, have some informal chat about that.
Sure.
So who will do the question from the audience? Yeah, Professor, Professor Fan again. Yeah.
Embrace the power, the moment. Of
Sorry.
the mic.
I'm wondering, you know, just thinking toward training the future generation of engineers, what kind of advice you would have for instructors to, like what kind of messages or skills you think would be important to incorporate into kind of the current existing engineering curriculum related to environmental justice or social vulnerability?
Yeah, that's a good question. I think a lot of the questions that you all have asked this afternoon speak to some of the curriculum and courses that ought to be developed, right? I think that we have to have courses around the ethics of engineering, right? We have Engineers Without Borders and some of those things, but even within borders and communities and investing in communities that surround campus, what does that look like, right? And what are, again, you know, these physical structures and infrastructures operate in the social world. What is that social, economic, political context in which these physical interventions will be operating, and making sure that engineering students understand that. What does community engagement as an engineer that works for the Department of Public Works or that works for a utility, what does that look like? And being able to instruct that while in an engineering program, as opposed to having to learn on the fly in real time while already working for a municipality. Those are the things that, and that's the type of training that I think engineers need and have to have moving forward, because again, the circumstances that I'm dealing with in Baltimore, between attention between public works and communities, and knowing how to navigate that, knowing how to engage communities, knowing how to lead times to be responsive when we do have contamination and things, and the ethics around that, right? There was an E. coli contamination in the drinking water. DPW learned of it on a Friday, didn't announce it until Monday, right? What are those, you know, ethical considerations and principles that have to be a part of the process and conversation of all of the things that I think communities and society in general is demanding of us as scholars and scientists and specifically engineers as we, you know, embark on this next journey and wave of scholarship and practice.
Thank you.
Our last question is going to come from Tom Hollenhorst, and they're asking, could the measures of infrastructure you described be used to better identify communities in need for directing EG40 funds and resources?
Yeah, I mean, that's ultimately the goal, right? And so, you know, the next iteration of my work related to the participatory assessment technique is like, how do we leverage the work of the community in terms of evaluating their infrastructure to then hand it off to departments of public works to inform the capital improvement plan, so that way communities are actually directing the funding in terms of investment for maintenance and rehabilitation. And so that's the goal. I mean, you know, I did that work in Houston shortly after, just before COVID. You know, I was brokering a partnership with the city for an initiative that they were calling Adopt a Drain, right? Where it was really sort of a low-hanging initiative of ahead of storm and rainfall events, encouraging residents to clear out the drains and open ditches. But I felt like it could be taken a step further in terms of, you know, during, before, and after rainfall events, having communities, again, leverage my technique to evaluate, derive a score, and again, use that to facilitate investment, whether that's coming from local tax dollars, the state, or the federal government.
Thank you.
Thank you all so much. Yep.
Well, I know, okay, some of you may have more questions, and well, okay, afterwards, feel free to hang around, you know, have some coffee and, you know, chat with Professor Marccus Hendricks. And really, okay, I want you to join me again to thank him for this great, distinguished lecture, and also please join me to congratulate Dr. Andrew Feldman again for this great honor for our newest, being our newest Straub Award winner. With that, I conclude this ceremony. Bye.